Okay, this is a short course on solid shape theory. I expect this to take a half a dozen or 7 lectures. This first lecture is starting late, so it'll only be 40 or 45 minutes long. The rest will be more like an hour. So we're concerned with the shape of surfaces. Here's a surface. Okay, it's got some kind of hump here in the middle of some kind of a furrow. It's got a concave region on the other side. Otherwise, it's convex. Okay. We're going to be interested in the idea of what's called a fitted frame. In the case of a surface, the fitted frame has, for a 2D surface in 3D, like this object, is going to be 2 vectors in the tangent plane and 1 normal to the tangent plane. We call that normal to the surface. Okay, so we're also going to be talking about space curves. Here's a space curve, and in this case, one of the elements of the frame is going to be tangent to the curve. It's going to be in the direction of the best fitting line. The second one's going to be orthogonal to it and in the best fitting plane to the curve at that point. And the third one will be the cross product of the other 2. So that's the general idea of a frame, that is to say a coordinate system. I'll define it more precisely in a moment, that are going to be fitted to generic surfaces. And I have to define the term generic. Okay. But we're going to be talking about 2D surfaces in 3D. Certainly that describes the variety of surfaces that we have in anatomic objects. We're also going to be talking about 1D curves in 3D, but we're also now and then going to talk about feature spaces, which are typically very high dimensional surfaces. And we're going to be talking about the generalization of these ideas to the shape properties of these abstract surfaces in feature spaces. So we need a definition of what I mean by a fitted frame, what I mean by a generic surface, and what I mean by local variation. Okay, local variation is really very easy. It's directional derivative. So we're going to be talking about, for example, the tangent vector, a unit vector in tangent to a point, and how it swings in the only direction you can walk, that is to say, along the curve in this case. Or in the case of 2D surfaces in 3 space, we're going to have a normal, and we're going to be able to talk about a walking direction. So we can walk off in this direction, or we can walk off in that direction, and we can walk in any direction from the point of around 360 degrees. And as we walk in that direction, the normal will vary, it will swing. We're going to be interested in the behavior of the swing of the normal as we walk along the surface, as another example. Okay? So I said we're going to do it for generic surfaces. And I'm going to be using this term generic frequently because, essentially because for all real world situations, those are the only ones we care about. The idea is that if you have a surface with a particular property, And then you take all possible smooth perturbations of the surface of infinitesimal size. So we can vary it a little bit up this way and a little bit down that way, and but by a very, very small amount, and by a smooth perturbation.
Well, what you mean smooth perturbation is like the local smooth perturbation, or the
everywhere smooth, everywhere on the surface, the whole surface. Well, we're only going to be interested in a locality of a point at any given time, but sometimes we'll talk about the whole surface. In any way, anywhere where it's relevant, the surface can perturb in a smooth fashion, meaning all derivatives exist. There's no infinite derivatives. So if I have a, whoops, put a brand new, okay, if I have this line or this curve in space, then that might be a smooth perturbation, but it's not infinitesimal, right? It deviates. The difference between the line and the perturbed line is a smooth function. Is a function that's you can take all derivatives of any order. Is that clear?
Yes.
Good. And I'm glad you're asking questions, because I want you to break in as soon as you have one. So you have the continuously infinite set of smooth infinitesimal perturbations. And if at most a subspace of lower dimension, typically that's a finite dimension. Any finite dimension is of lower dimension than infinite dimensions. If the property holds everywhere except in a lower dimensional subspace, we say we say that the property is generic. And so to talk about a generic surface, well, let's talk about, for example, a straight line. Is straight line generic? Okay, does it have, the property we're talking about is it has the same tangent everywhere. Okay, well, here's a small perturbation of it. Is that a straight line? Nope. What about this one here? Is that a straight line? Nope. It turns out that 0% of the time is a perturbation of a straight line still a straight line. Okay, it's a lower dimensional subspace of perturbations. The only perturbations that would leave things as a straight line would be what the smooth one that gives you this, or the smooth one that gives you that, or maybe the smooth one that gives you this diagonal. But that's only a two-dimensional subspace of possibility. Translation, a translation, and maybe a slight slope change. So that's a two-dimensional subspace that leaves it as a straight line, but otherwise, all the other ones aren't straight lines, and so straight lines aren't generic. Okay. Moreover, neither is any flat n-dimensional thing. So a flat surface isn't generic. Okay. Doesn't matter. You can never a straight line for a real object is a figment of your imagination. You can't make a straight line because we can't measure straightness to within epsilon accuracy. And so you might just as well approximate the straight line by a curved line to within some tolerance. And so the same goes for flat surfaces. The same goes for things with corners. Things with corners are not, even if it's curved, you have it here and I have a corner and I have another curved piece, that's not generic either, because all the smooth perturbations of this will not have this pointy property. Okay, almost all of them will be smooth. And the result is that, but that's all right too, because there's no pure points in the real world. That we can't measure points to an adequate accuracy to be sure that it's a point. It might just as well be slightly curved. Okay, so instead of this sharp thing, we might have a relatively sharp turn, but not a point.
In this case, we make the sharp turn as a round and smooth turn. Then this shape has the property of generic.
Yes, the smooth one will have properties that are generic, whereas the pointy one doesn't. So to make a long story short, we're going to be talking about smooth surfaces, and if we want to deal with corners, we're just going to talk about places that have very high curvature, but not infinite curvature. Okay, so that now we have a general notion of generic. Later, we're going to talk about the generic other aspects of genericity, but this is good enough for now. The mathematicians, the singularity, genericity is a property studied in the field called singularity theory, and that's where you can find a very careful mathematical definition of what it means to be generic.
So in my rough understanding, it's like generic somehow is, so every smooth surface is generic. Is that true?
Well, we're going to be talking about more than smooth surfaces. So say, for example, okay, so you can show that for every convex object, in fact, for every closed surface, whether it's convex or not, there exist points on it that are locally spherical, that have same curvature in every direction, like a sphere does. Okay? That kind of a point is called an umbilic. The question is, are umbilics generic? And the answer is, well, let's look at all the infinite perturbations of this surface and see whether within an infinitesimal distance of where the umbilic was, you still have an umbilic. And the answer is yes, you will, in all but a minority subdimensional set of cases. So umbilics, the umbilic property is generic, we say. Okay. Okay, so let's be careful about the word frame. A frame is a right-handed tuple of orthonormal vectors. Okay, so in 3 space, here's a frame, right? It has a first vector, a second vector, and a third one, which is the cross product of the first two, right? It's a right-handed coordinate system. Okay? Each one of these frame elements are unit vectors. A unit vector, unit vector, unit vector. 3 normal, that's what orthonormal, that is to say, each is orthogonal to the other, and each is a unit vector. Okay? I've already talked about what a fitted frame is. You take one of these frames and you have a particular locus you're interested in, like a space curve or like a surface, or like a scalar function of 3 space. Okay? And we can fit it in the sense of, well, for a scalar function of 3 space, this direction might be in the gradient direction of that scalar function, and these two are in the along the level surface, a tangent to the level surface of that scalar function at that point. That's a fitted frame. For a 2D surface, we can have a fitted frame where one of the elements, typically the one that's called the third, is the normal, and the first and second are in the best fitting local flat mathematical surface plane. Okay, so that's That's one. So is that one. So is that one. So is that one. As long as this one stays normal. Okay. We'll later put some constraints on the other two, so that the fitting is even tighter. That is to say, at any given point, we specify not only the normal direction, but which are the two special directions in the tangent plane. The same thing is going to happen for a space curve, where we have a fitted frame. One of the directions is the best fitting line. One is the one which, together with the first, span the best fitting plane, and the third one is the cross product of the other two. Okay, so now we have an idea of what a fitted frame is. Okay, and so as we move along the curve, the fitted frame is going to do something. It's going to rotate, in fact. If we move in some direction on the surface, the fitted frame is going to rotate. If we move in a different direction on the surface, it's going to rotate somehow differently. And we're going to be interested in those variations of the fitted frame as we walk along a surface, typically. Now and then we'll talk about a curve. Okay? So in this first lecture, we're going to be focusing on the normal, okay, one of the elements of the fitted frame. And in fact, a major part of this lecture series is going to be on that, just the behavior of the normal, okay? But we'll also later talk about the behavior of the other special elements that are of the frame that are in the tangent plane. Okay, and so we're going to be, for a space curve, we're actually going to be talking about the behavior of the tangent, not the normal, as we walk along. But for a surface, we're going to be talking about how the normal swings as we walk in various directions from a point. Okay? Well, the first thing, a mathematical property that is worth understanding is that if you take a unit vector of unit length and rotate it by a little theta, where theta is infinitesimal, okay, very small, that the difference between the two, which is that vector, is orthogonal to the original vector. Okay, so what I'm saying is, if you take any first derivative of a unit vector, it's going to be orthogonal to the unit vector itself. And since the normal is a unit vector, as we walk along the surface, the derivative of the normal, I'm going to write sometimes this: the derivative for some walking direction on the surface of the normal. Okay, so that's the directional derivative of the normal for walking in the v direction. Sometimes you'll see, and we'll see why I'm going to use this, sometimes I'm going to write that this way: d with angle brackets v of n. And that means the same thing. That's just two notations for the same things.
So I have one question about the 3D curve. So for the curve, do we need to specify the direction, because we only can walk in one direction
at any given point? So for the curve, we're going to be interested in dt at that point of t. Right?
Yeah.
And if we call the second frame element, which is the one that with the tangent forms the best fitting plane, and we call that the curve normal, which is what it is called, we may be interested in dt of that curve normal.
Yes, two curve normal. because like you have two directions in the tangent plane.
I mean,
In a 3D curve.
the normal, in what, the normal and its opposite sense? Is that what you meant by a different?
Yeah, except that we have a tangent direction, which is along the curve direction. Yeah, we have the other two directions, right?
So no, there's a best fitting plane to the curve, and this plane will have only this or this as its direction. That's a change in the sense. And it turns out that you will see later that the normal is defined in such a way that only one of those senses are possible. Okay, but we'll get to that later. Okay, so for a curve, we're going to be interested in things like dt of t and dt of n, or maybe of the third cross product vector, which is called the binormal. And we'll be interested in dt of b, but always for walking in the t direction, because there's nowhere else you can walk if you want to stay on the curve locally. For a surface, v has to be in the tangent plane. But you can only walk locally in directions that are in the tangent plane. And therefore, v is a whole circle of possible walking directions, right? But every single one of these is going to be normal to the thing it's taking the derivative of. So this is going to be orthogonal to t, and this thing is going to be orthogonal to n, and this thing is going to be orthogonal to b, and this thing is going to be in the tangent plane at that point, right? So walking direction is going to be in the tangent plane, and the local swing rate of the normal, which is what this measures, is also a vector in the tangent plane. Okay? Now, what does that mean? Well, let's get ourselves a tangent plane to a surface. Okay, so here is one. It's supposed to be flat. And I have two vectors, and I'm going to let one of them be the walking direction, and the other one be orthogonal to it. So now my fitted frame is going to have the normal to the surface as one of its vectors, the walking direction as another one, and the orthogonal to the walking direction as the third one. Okay? So we're going to have the tangent plane is spanned by v and v perp, where both of those are in the tangent plane. Okay? And so we can write any vector that's in the tangent plane as a linear combination of v and v perp. And so we're going to talk about this swing vector as we walk along the surface as a function of v and v perp. So here we have, we're going to walk, let's do it this way. We're going to walk in some direction, like this one here, v on the right. There's v perp. And as the normal swings, it's going to swing into some direction. Another way of thinking about that is you're going to have a hinge about which it swings, and it's going to swing into the direction orthogonal to the hinge that it's swinging about. Okay, the hinge is just the axis of rotation of that normal vector. Okay, so we have this hinge direction in the tangent plane. We have the direction orthogonal to it, and the normal is going to swing in that direction orthogonal to the hinge. Well, that vector is going to be a vector, that hinge vector, that this vector dv of n, that swing vector per unit walking distance, is going to have a component in v and a component in v perp. Okay, so let's get some of this erased. We're talking about for a surface now. We'll get to the space curve later, but okay, we have this dv of n, and what I'm now saying is this is going to be alpha times v plus beta times v perp. And also we know that, okay, so sorry, just that. So we can subdivide the swing vector, the change in the normal, as something times v plus something else times v perp. Okay, so these guys get a special name. This guy gets the name the normal curvature. You see that on the slide. Okay, and it's simply the nosedive. That is to say, if you had pure walking, if this was my walking direction here, and I had a pure nosedive situation, so it swung entirely in this situation, you'd see how this vector swings into the walking direction, or possibly in this walking direction. Now we need to be able to talk about positive nosedive and negative nosedive. And for reasons that are not worth discussing here, it turns out to be conventional to call positive nosedive when the normal falls away from the walking direction, and negative when it falls into the walking direction. Okay, so here's negative curvature, negative normal curvature, and here is positive normal curvature. Okay, so so this other component is called the geodesic torsion, or colloquially the twist. When we walk in this direction, if we had pure twist, the normal would swing this way. We walk this way, and we walk this way, and the normal swings that way or that way. That's the component in v perp. This is v. This is v perp. We have normal curvature and geodesic torsion, or twist. We twist about the walking direction. But in general, we have alpha amount of nosedive and beta amount of geodesic torsion, of twist. So when we walk in, for example, this thing swings this way, we're going to have a vector in this direction that's going to have a component in the v direction and also a component in the v perp direction. And those are going to be respectively the normal curvature and the geodesic torsion.
So, regarding geodesic torsion, do we have a positive geodesic torsion and negative geodesic torsion?
Yes, I'll talk. Okay, so this is normal curvature. Yes, and it has to do with the right-handed coordinate system. So if I have a vector, if this is the walking direction, this guy is 90 degrees from it in such a way that that its cross product is the normal. Then this direction, if we put another way, the normal cross product this has to be the second direction. That's fixed. if the normal happens to fall this way, then it will have positive. I'm sorry, it will have a negative component in this direction, right? So in other words, when so it has to do with the sign of the component. Okay. Okay. So. Okay, so that's the setup for all the things that we're going to talk about now. Okay, and so at this point, I'm going to switch to my other slide set. So how do I do that? Just okay, fine. So. What we've said is that for every point on a smooth surface, for every walking direction at that point, there's an associated normal curvature and associated geodesic torsion. Right? Now, we're going to be interested in one very special case and one other also special but not as special case. And the first special case is the pure nosedive situation. The one where beta equals 0. That is to say, it's when you walk in this direction, it swings about the V perp as a hinge, or equivalently swings into or away from the walking direction. Okay, so that's pure nosedive. Yeah. Pure nosedive. Okay, that's to say beta is equal to 0. Okay? A direction that has pure nosedive is called a principal direction. Okay? A principal direction is a direction of pure nosedive. For those who are listening to this on video, and for Yadzong who's listening to it here, I want you to notice that that's the verb principle. Don't spell it with an LE. That's a noun. It's not the same not the same word. Okay, we have a principal direction. The impressive thing is that you can prove that for every point on a smooth surface, there are a pair of principal directions and they're orthogonal to each other. Okay, and we'll talk about how that comes to pass. But right for the moment, at every point, there's some walking direction that's principal. And not only that, 90 degrees from it is also principal. Okay, so we'll call this principal direction P, and call one of them P1, and another one P2, which is orthogonal to P1. They're both in the tangent plane, and both are principal directions. And for every point, there exists such a pair. Okay? There'll be a limited number of points for which there are more than 2. In fact, an infinite number. Every direction will be principal. Those will be the spherical points, the points that are locally spherical, but where the surface is locally spherical. But fine, even then, you can pick out a pair of orthogonal ones. So there's always a pair of orthogonal principal directions. Okay? And this will lead us to the notion of a principal frame. So now we have, at every point, not only the normal, but now we're going to specify that the first principal, the first direction in the tangent plane is a principal direction, and 90 degrees from it is also a principal direction. And so now we have what we will call a principal frame made out of P1, P2, and the normal.
Okay, but how to distinguish between P1 and P2?
We'll talk about it in a moment. We're going to. First of all, it turns out that if a direction is principal, so is the opposite direction, just the opposite sense. And so we're going to in a minute talk about something called principal curvature, and we can choose on the basis of which has the larger principal curvature, for example. There are a variety of situations where we choose differently, but that's an example of how we might choose between P1 and P2. Okay? Okay, so we have a principal frame. If deviate, okay, so what we're saying is if we walk in any of the principal directions and we look at the normal, what we will have is something of the form alpha P1. And that's also true for P2, right? It says the swing of the normal is only into the principal direction. It's pure nosedive. The beta is 0. This alpha gets a name, and it's called the principal curvature. Okay? Associated with the principal direction 1. And so it's written kappa sub 1. It's the rate of swing of the normal as you walk in that principal direction. It's a amount of rotation, an angle per unit direction measurements. It's measured in radians per unit step. Okay. Similarly, if I put 2 here, I'm going to have a 2 here. I have the other principal curvature, right? If I walk purely in the other principal direction, okay, so here I am. Here's one of the principal directions. So if I walk in this direction, I get pure nosedive. I'm going to get the rate of rotation is going to be of this normal is going to be the first principal curvature. If I walk in this direction, it's also principal. So it's going to also have a rate of scalar rate of rotation. That's going to be kappa 2. And they will be signed according to the convention we talked about. They can be both positive. They can be both negative. One can be positive, one can be negative for either one. The convention that we'll take most of the time for most of this is that kappa 1 will be greater than kappa 2 if they're not the same. So we'll call the first principal direction the one of greater rate of swing. Greater in the mathematical sense, not greater in magnitude, but greater in, a positive number is greater than a negative number, right? Okay, and then we're going to have the special situation where kappa 1 equals kappa 2. And indeed, those are the spherical points. Those are if you're on a sphere, no matter what direction you walk in, you swing with a kappa, which is 1 over the radius of the sphere. In fact, that relationship has to be always held in mind, that 1 over any kappa is the associated so-called radius of curvature. Or equivalently, 1 over the radius of curvature is kappa. Okay, so any direction at a sphere, I swing at the same rate. And in fact, every direction on a sphere is principal, pure nosedive. And so every kappa is the same as the orthogonal the orthogonal direction, namely 1 over the radius of the sphere. And so at a spherical point, and only at spherical points, are kappa 1 equal to kappa 2. These are the spherical points. And the fancy mathematical name for them is umbilics. Okay. Okay, so now we have directions that are pure nosedive directions, and we're going to have this principal frame. Now, the second most important directions, other than the principal ones, are the ones of pure twist. They're the directions when you walk in that direction, there's no nosedive. All that happens is this. So they're the ones where alpha is equal to 0, whereas the principal directions are ones where beta is equal to 0. Okay? And we will see that that can only happen. Okay. So pure twist direction gets a name. It's called the asymptotic direction. It's a pure twist direction. And it only can happen if kappa 1 and kappa 2 have opposite sign. We'll see that there exist no asymptotic directions when either kappa 1 and kappa 2 are both positive, or kappa 1 and kappa 2 are both negative. Okay. So this brings us to the closing part of this lecture, because we got something else coming up here, I think at 2 o'clock. And that is these combinations of kappa 1 and kappa 2, the 3 possibilities, both positive, both negative, or 1 positive and 1 negative. If you're at a point surface such that in one principal direction you're falling forward, that's negative nosedive. In the other direction, you're also falling forward. You can show that for every direction that you might walk in, the nosedive is going to also, I said negative and negative. You fall forward, that in every direction the nosedive will be forward. We'll show that shortly. And so what would you call a point where the nosedive, what adjective would you use to characterize a point that the nosedive is negative everywhere? Well, the adjective is convex. That's a convex point. It's a point that no matter what direction you fall, locally it's curved downward. The fancy mathematical say is a little ways off. If you connect any such 2 points, it'll cross through the object rather than outside of the object. I'm about to stop, so welcome to join us. Okay, so what about if they're both positive? That is to say, if they fall backwards in both directions. What's that? Okay. That's concave. Okay, and the third possibility is what's called hyperbolic. Okay, and so this is the last bit of this lecture. I'm going to erase some things here and write that down. So this situation that I described here is the situation where the surface is said to be hyperbolic. What it is, think about walking in this furrow. When you're walking along this direction, it's falling forward, but when you're walking along that direction, it's falling backwards. Okay, that's a hyperbolic location. If kappa 1 and kappa 2 are both greater than 0, it's concave. And if kappa 1 and kappa 2 are less than 0, the point is called convex. Okay? What we said about these asymptotic directions is they only happen in hyperbolic places. Well, we haven't quite finished the story because we haven't talked about the situation where kappa 1 equals 0 or kappa 2 equals 0. That or is an exclusive or. Why not kappa 1 equals 0 and kappa 2 equals 0? Because it's non-generic. That's the pure flat point, and there's no, it is a completely non-generic situation. It never happens with enough dimension to matter to us. Zero probability we'll ever see such a thing. Okay, so we're going to be worried next time to start talking about the situation where one of them is 0 and the other is either positive or negative. But we're done for this lecture right now. Okay, why don't you turn the video off?